Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 23 in which I'm going to discuss degenerate perturbation theory uh, and the time dependent perturbation theory both. Okay, so and also I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, so I'm going to start now. Okay, so degenerate perturbation theory. Okay, degenerate degenerate perturbation degenerate perturbation theory. Okay, so degenerate perturbation theory, this I'm going to explain by example. So I'll solve one question and which will help you to understand degenerate perturbation theory. Okay, so the question is, a system with a system a system with a system with unperturbed Hamiltonian unperturbed 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 Hamiltonian. So I'll write unperturbed Hamiltonian first. Okay, so unperturbed Hamiltonian is given, that is h equal to epsilon naught 300 030 and 005. Okay, so a system with unperturbed Hamiltonian h equal to epsilon 0 or E0 300 030 005. Okay, is subjected is subjected to perturbation subjected to perturbation h dash equal to epsilon upon or E upon 100, epsilon upon 100, is epsilon naught or E naught upon 100. This is 300, apologies, so this is 010 100 and 000. So this is the unperturbed Hamiltonian given, and this is the perturbation. Okay, is subjected to perturbation. This the energy up to first order. Okay, the the energy up to first order. Energy of first order. That, so now with this question, I will explain. This is an example of degenerate perturbation question. Okay, I'll explain degenerate perturbation theory by this example. Okay, so this is unperturbed Hamiltonian given, and this is the perturbation given. Okay, so we have been given that unperturbed Hamiltonian h equal to epsilon. We have already studied. Okay, guys, so you can check my previous lecture. So this is 3 0 0 0 3 0, and 0 values are eigenvalues are 3 E naught. We can say it's E naught. Okay, 3 E naught, comma 3 E naught, comma 15 E naught. Okay, so these are the eigenvalues and these are the energy of the Hamiltonian, right? Uh, and this energy is before perturbation. Okay, so here you can you can see that there are two energy which are equal, that is 3 epsilon 0 and 3 epsilon 0, right? So it means this is the case of degenerate perturbation theory, right? So because the energy is degenerate here, right? Two equal energy, so it is the case of degenerate perturbation theory. Okay, so now we'll find out the first order correction, right? And this is a degenerate case, so we'll use degenerate perturbation theory to solve it. Okay, well, now these are the eigenvalues, and eigenstates are eigenstate eigen eigenstates eigenstate or eigenvector are this one. Okay, state are get 1 equal to 1 0 0, okay, comma state 2 is 0 1 0, okay, and state 3 is this is 0 0 1. Okay, these are the eigen state. Okay, for 1 this is 0 1 0 0, 2 it's 1 0 0, and this is 0 0 1. Okay, so these are the eigenvectors. Okay, now zeroth order correction, you can see zeroth order correction. Okay, so there is no zeroth order correction is this one. If you talk about, this is the energy eigenvalues, or we can say this is the energy eigenvalues before perturbation. Okay, or we can say uh, zeroth order energy correction. Okay, zeroth order energy correction. I'll write it as well. Zeroth order energy correction. That is the actual before Hamiltonian, right? So this is 3 E naught and 3 E naught and 15 E naught. Okay. Now we'll find first order correction. Okay. So we can see here, you can see this is the degenerate case and this is not in non-degenerate case, right? And we know how to find the first order correction in the energy of non-degenerate case, right? So the first is first order correction, first order correction, first order correction. Okay, and this is the case of non-degenerate case. Okay, this is non-degenerate, this is the non-degenerate case. Okay, because 15E is a non-degenerate case. Okay, so first order energy correction for this energy we are going to find. Okay. Okay, let me just check whether I'm audible or not. And this is the case of non. Yeah, I am audible, so I'll proceed further. Okay, so this is, we know that eigenstates, right? So this is the third energy, right? So this is going to be non-degenerate case. So this is going to be E31. Okay, so this is the energy third, right? E31, first order correction in energy E3, right? This is E3, E1, E2, E3. Okay, we can say E1, E2, E3. Okay, so E31, the first order correction in the energy, this it is going to be this we know, right? That is 3 H dash 3, right? These states we know here. I'm explaining each and every step very carefully, okay? So I would request you just pay attention and understand, because uh, you can get questions from degenerate perturbation theory in your examination, okay? Well, so this is going to be, this we know, right? This is 0, 0, 1, and H dash is given, right? And that is given here, E0 upon E0 upon 100. So this is E0 upon 100, and this value is uh, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, and 0, 0, 0. Yeah, and this is three state is 0, 0, 1. Okay, we'll solve it, guys. So this is matrix multiplication. We can easily solve it. So this is going to be epsilon upon 100, and be 0, 0, 1. Epsilon upon 100. Well, I'll solve this, right? And we know matrix multiplication. So this is going to be 0 plus 0 plus 0. Okay, and this one, this row with this column. Okay, so this is 0 plus 0 plus 0, and this one is 0 plus 0 plus 0. Okay, so this value is going to be 0, right? And this is going to be 0, and 0 with 0, this is going to be 0. Okay, so E31, the first order correction in this energy is 0. Okay, so this is the so there is no so first order correction in this energy is 0. Okay, now second, now we will solve degenerate case. Okay, degenerate case. Degenerate case. Degenerate case. Degenerate case. So degenerate case. So we have energy, right? This is so degenerate cases. We have energy 3 E0 and 3 E0, right? This one. So for degenerate case, the first order energy correction. Okay. First order. First order energy correction. First order energy correction. First order energy correction in degenerate energy. In degenerate energy. Okay, the first order energy correction in the degenerate energy, and that for degenerate case, this is a formula, guys, you need to note down. Okay, so delta H is going to be this one, 1 H dash 1, 1 H dash 2, 2 H dash 1, and 2 H dash 2. Okay, this you need to note down, guys. Okay, very important, this one. So the first order energy correction in degenerate energy, the first order energy correction in degenerate energy is this. Okay, so now we'll find this value, this value, this value, this value, one by one. Okay, so the 1H1, so value of 1 H dash 1. Okay, 1 H dash 1. Okay, this value will find. So this is going to be one value we know, right? This is one is 100. This is like I have shown you here. This is 1, right? 1 0 0. This is the cat form. Bra form is 0 0 1. That will be in the row. Similarly this, right? This you know. Okay, so this is, and value of h naught we know, e naught upon 100, 0 1 0 1 0 0 0 0 0, right? This we know. And value of 1 is 1 0 0. Okay, so you will solve it. So this is, first we will solve this, right? So this is going to be 0 1 0 0 epsilon E0 or epsilon E0 E0 upon 100. Okay, this value will multiply. So this is going to be this one with this, right? So this is 0 plus 0 plus 0, and this is 1 plus 0 plus 0, and 0 plus 0 plus 0. Okay, so this is going to be E naught upon 100, and this is 1 0 0, and this is 0 1 0. Okay, and then we'll solve it. So this is going to be E naught upon 100, and this is 1, this with this, right? And this is going to be 1 plus 0 plus 0, right? And not upon 100. Okay, this is E, right? Okay, E naught upon 100. So 1h1 we have found. Okay, 1h dash 1. Now we'll find 1h dash 2. Okay, 1h dash 2. So this is going to be one value we know, right? This is 1 0 0. Okay, and h dash is 0 1 0 0 0 1 0, and this is 1 0 0 and 0 0 0, and this is 1 0 0. Okay, we'll solve it. So this value is going to be, I think we have made some mistake here. What mistake we have done? 0 1 0 0 0. Okay, so this value is going to be 0. Okay, so similarly here we'll solve this one. This is 2. 2 means 0 1. Okay, so now we'll solve it. 0 0 0 E naught upon 100. Okay, and this is with this, right? So 0 plus 1 plus 0, and this is with this 0 plus 0 plus 0 0 plus 0 plus 0. Okay, so this is going to be epsilon 0 upon 100, E naught upon 100. Okay, E naught upon 100, 1 0 0, and this value is 1 0 0. Okay, we'll solve it. So this is going to be epsilon upon 100 into this with this, right? So this is going to be 1 plus 0 plus 0. This value is epsilon upon 100. Okay, now there is symmetry, guys. Okay, in this type of question there is always symmetry, so you don't need to solve other remaining two. If 1h1, this one 1h dash 2 is this value, then 2 2h dash 1, this value is also be the same. Okay, you can calculate it if you want it, but because of symmetry this value is same. Okay, 1h1. Okay, and 1h dash 1 value is 0, so it means 2h dash 2, this value will also be 0. Okay, so because of symmetry, so this so now we've got the value. Now we'll put this value in equation 1, we can say this one. Okay, so delta is going to be, therefore delta h value is This is 0, 1h1, right? 1h dash 1, 0. We have found it, 0. And 1h2 we have found, that is epsilon upon 100. And this value, 2h1 is also same, that is by symmetry. We can also find out it. This is the delta H. Now what we are going to find, it is eigenvalues of this, right? This is the Hamiltonian. This is the energy in matrix form. So this then delta H minus going to be delta H minus AI, going to be determinant of delta H minus AI is going to be 0, right? And so this is going to be 0 minus lambda and epsilon 0 upon 100, and epsilon 0, I mean to say E naught upon 100, okay? It's E naught upon 100, E naught upon 100 into 0 minus lambda not equal to 0, right? Determinant. Okay, so this value is going to be now lambda square equal to epsilon upon 100. This means lambda value equal to plus minus epsilon upon 100, that is E equal to plus minus epsilon upon 100, okay? Or delta E equal to, you can see delta E, okay? These are the energy eigenvalues, right? So now we can easily found. So now, so energies are going to be, the E1 is going to be, E1 is 3 E naught. The energy, first energy is going to be 3 E naught plus this one, epsilon upon 100, epsilon upon 100. E2 is going to be actual energy, that is 3 naught minus epsilon upon 100, and E3 is actual energy 15 E naught plus correction, first order correction in energy, first order correction in this energy is 0, we have already found, right? So this is 15 E naught, okay? So these are the answer. This is how we solve questions related to degenerate perturbation theory, okay? So very simple. So it's very simple actually, okay? So first you need to find out the eigenvalues, right? And then you will get the degenerate eigenvalue, and these will be degenerate eigenvalues of energy, okay? And then you will get first order correction to the for non-degenerate case, you will get the energy which we know. And then for second, from there we will find the value of delta E, and then the actual energies, the correction in first order energies are going to be because this is 0 we've got, so this energy will remain same here. These are the values, right? So now we'll add this and subtract this. So these are the first order correction in the energy. This is in degenerate energy and this energy, right? I hope you understood it, right? Very good. And now you can easily solve questions related to degenerate perturbation theory, okay? So this is how we solve questions of degenerate perturbation theory. Well, next is this one, time dependent perturbation theory, okay? Time dependent perturbation theory we are going to discuss, very important. We'll solve question as well, okay? So time dependent time dependent time dependent perturbation theory, okay? Perturbation theory, okay? Time dependent perturbation theory. Okay, time dependent perturbation theory. So here the perturbation depends on time. Okay, I'll show you. So we know the total Hamiltonian is going to be h naught plus h dash, which will be function of t. Okay, so this h naught is time independent. Okay, this is uh, time independent. This is time independent, and this is h dash, which is a function of t, means this is time dependent. Okay, so here the h dash will depend on time. That is perturbation will depend on time. Okay, so we can denote initial state I. Okay, with ei. Okay, and we can denote final state here, final state with ef. Okay, well, this is final state. Okay, next uh this one. So here we'll find transition probability, guys. Okay, transition probability. So this is pfi. We denote it by pfi, transition probability, right? And this value is very important. You need to note down. You'll get questions. Okay, there are many questions which were asked in CSIR, NET, and other exams. Okay, so this is pfi is mod of cfi whole square. Okay, mod square of cfi, and where cfi value is minus iota upon h cut root very important formula. Okay, minus iota upon h cut root 0 upon integration 0 into t 0 to t. This is h dash fi. Okay, and e to the power minus iota omega fi t dash dt dash. Okay, so this is the cfi. Okay, this is minus iota upon h cut 0 integration 0 to t. This is h dash fi into e to the power minus iota omega fi t dash into dt. Okay, so this is the one. So here I'll tell you this one. So here the h, this value is h dash this one, final state with h dash initial state. Okay, so this is the h dash fi value. Okay, and omega fi value is ef minus ei by 2. Okay, my apology, this is ef upon ei upon h cut. Okay, ef upon ef minus ei upon h cut. Okay, so this is the value of fi. Okay, so now pfi, value of pfi is going to be transition probability. Pfi, this is going to be mod square of minus iota upon h cut, because this is cf square, right? Mod square of cfi, right? This is going to be iota minus iota h cut integration 0 to t h dash fi e to the power minus iota omega fi t dash dt dash. This is mod square. Okay, so this is the value pfi equal to minus mod square of minus iota upon h cut integration 0 to t h dash fi e to the power iota omega fi t dash dt dash. Okay, and here I have already explained. This is this one, h dash fi is the product of f h dash I. Okay, and these are the initial and final states, right? This one, and yeah, and omega fi value is this one, ef minus ei upon h cut. Okay, This is very important formula, guys. We'll solve questions which were asked in NET, CSIR NET. Okay, very important. You need to note down and memorize it and solve questions using this formula. Okay. Okay. Next. Next is this is transition probability. Okay. PFI is transition probability. Okay. Okay. Next is we are going also if now we are going to solve if the h dash is not dependent on time. Okay, means it is if it is a constant perturbation. Okay, constant perturbation means that does not depend on time. Okay, then what will be the transition probability that we are going to find. Okay, so this is the transition probability, very important formula you need to note down. Okay, next is as a question. Okay, I'm solving this question. Okay, so h dash t, this is the perturbation which is dependent on time. Okay, h dash t is given v naught. Okay, v naught when t dash is between 0 to t. Okay, 0 to t and 0 otherwise. So here you can see h dash t is v naught, which is constant, right? And which is in constant means independent of time. So we can say constant perturbation. Okay, constant perturbation. So if this is the case, means constant perturbation is given. Okay, constant perturbation which is which doesn't depend on time. Okay, because it's a constant, right? In that case, what will be the transition probability that I will explain. Okay, so we know here formula, that is CFI, that we know, minus iota upon h cut integration 0 to t h dash fi uh, right, h dash fi e to the power minus iota omega fi we know, or we can write this like this. Okay, CFI, this is going to be minus iota h dash integration 0 to t h dash fi values we know, right? That is f, we can write f v naught h dash t is given, right? So h dash fi is f v naught, because this is the perturbation, right? F v naught I, right? This is given, right? And e to the power minus iota omega fi t dash dt dash, right? This is the CFI, right? So now this is going to be CFI value is going to be, we can write minus iota upon h cut, and this we can write this is h dash fi, right? And this is v naught, right? So we can write this vfi, right? Vfi, and this is vfi going to be vfi value is vfi, right? So this is the s dash fi, and this is v naught, right? So we can write vfi, this value minus iota omega fi t dash dt dash, right? So we'll solve it. So minus iota upon h cut vfi, and this is going to be e to the power minus iota omega fi t dash upon minus iota omega fi and 0 to right? We have integrated it, this part. Okay, so this is going to be minus minus will get cancelled, so iota upon h cut vfi, and this value is going to be e to the power minus iota omega fi t minus 1. Okay, so this is 1 upon, this is omega fi. Okay, this is the one. So now here I'll show you something. Okay, this we know, this e to the power minus iota x. Okay, e to the iota x value is, this is e to the power minus iota x. Okay, e to the power minus iota x value, we know that is going to be, here we can take e to the power iota minus 1, e to the power minus iota minus 1. This value we can write e to the minus, I'll write here. Okay, so this I can write like this, is going to be, I'm writing just below it because there is no place. So this is, we can write e to the power minus iota x by 2, we can take common, and this is going to be e to the power minus iota x by 2 minus e to the power iota, right? We can write this, we can take, and if you solve it, we'll get the same value, right? And now we can write this iota x by 2, we can open it, right? E to the power iota x by 2 in sine and cos, so this value is going to be 2, cos part will get cancelled, 2 iota sine x by 2, we can do it, right? The same thing I'm applying here. Okay, here on h cut vfi. Okay, and this is going to be e to the power minus e to the power minus e to the power minus iota omega fi t by 2, right? T by 2 minus, this is minus, right? Okay, minus 2 sine omega fi t by 2. Okay, I can write using the same. Okay, so now h cut omega fi, right? H cut omega fi, this is upon omega fi, right? Omega fi. Okay, h cut omega fi, and this value is going to be the 1, right? So this is going to be e to the power minus iota, e to the power minus iota omega fi t by 2 into minus 2i sine omega fi t by 2. Okay, this we can write. So this is the one, right? This is good. Now so now we can write cfi mod square, that is pfi square, right? The transition probability. Now we know the transition probability formula, pfi, that is going to be this is going to be the mod of this. Okay, so mod of this is going to be vfi square upon h cut square, or we can write t square. Okay, and there would be 4 as well, 4 t square, and this is going to be sine omega fi t by 2 upon sine, my apologies, so this is omega fi. omega fi t square. Okay, how we have multiplied by t square and divided by t square. There is a reason of doing that. Okay, so t square and 4 is here, right? Or we can write pfi equal to vfi square t square upon h cut square into sine, this is square again, omega fi t by 2 upon omega fi t by 2 whole square we can write, because 4 will take in this denominator, right? So this is omega fi t by 2 whole square. Okay, 4 we have taken in the denominator. So this is very important formula, guys. You can solve questions. So this is the transition probability when there is a constant perturbation. Okay, then that time this is the uh, formula, very important formula, guys. You need to note down. We this is mod of vfi square, mod of vfi square. Okay, this one, this one. Okay, yeah, this is mod of vi square. This is mod of vfi mod square. Okay, so vfi mod square, vfi mod square. Okay, so this is very important formula. You need to note down. You will solve questions using this formula. Okay, well, now we'll study two different cases for this. Okay, this is equation number 2. We can say two different cases. Okay, the first case is case 1. Okay, case 1 is if omega fi value of omega fi. Okay, if omega fi tends to 0. Okay, tends to 0. If this value tends to 0, so it means this value transition probability is going to be pfi is going to be vfi mod square t square upon h cut square and limit t tends to 0 sine omega fi t square by 2 upon, this is sine, this is t by 2 upon omega fi t by 2 whole square, right? Since we know limit, I have already explained this in my mathematical physics lecture. So limit t tends to 0, or we can write this one, limit theta tends to 0 sine theta upon theta, this value is 1, or limit theta tends to 0 sine theta upon theta whole square, this value is also 0 we know. Okay, so this value pfi value is going to be, so vfi mod square t square upon h cut square, and this value is 1. Okay, so pfi value is going to be this into 1. Okay, so in that case pfi, if t tends to 0, then pfi is going to be pfi is going to omega fi tends to 0, guys. Omega fi tends to 0, omega fi tends to 0. Okay, omega fi tends to 0, so this value is going to be 1. Okay, so this means pfi proportional to t square. Very important, guys. You need to note down. You will solve questions using this. So pfi, if omega fi tends to 0, then pfi is proportional to that, transition probability is proportional to square of time. Okay, well, this is the one. So this is t tends to 0, not omega tends to 0, t tends to 0 guys. Okay, t tends to 0. Okay. Second case. Case second. Case second is if t tends to infinity. Okay. In that case, first RFI value is going to be RFI value is going to be uh, PFI by T. So the PFI we know that is transition probability. RF is rate. Okay. So this is rate of transition. Okay. Transition rate. Okay. Transition rate. Okay. So transition rate is transition probability upon time. Okay. This you need to note down. Okay, so now we'll find out RFI first. Okay, first we'll find RFI, then we'll find PFI by multiplying RFI with T. Okay, very simple. So this is going to be RFI, and here you need to know one thing. Okay, that I'm going to write in limit T tends to infinite sine sine square yt upon pi y square t. Okay, if this value is always delta y, that is Dirac delta y. Okay, this you need to note down because we'll use it. Okay, so limit t tends to infinity sine square yt upon pi y square t equal to delta y. Okay, well, so then RFI value is going to be this one, mod VFI square t square upon h cut square t. Okay, and this is sine omega fi t by 2 upon omega fi t by 2 whole square, right? This one. So this we can write here t square h cut square t, because RFI equal to RFI equal to PF upon TI, right? PFI upon TI, right? This, and this is going to be sine omega fi t by 2, the t tends to 0, right? So this is limit t tends to infinity sine omega fi t by 2 upon pi omega fi by 2 whole square t square. Okay, right? T square will get cancelled. Okay, this one. So here you understand. T square will get cancelled. T will be here, right? And we can use this formula. This one. Limit t tends to infinity sine square yt upon delta y square t. This is delta y, right? So here instead of y, the value is y is omega fi, right? Omega fi by 2 into t. We can write this omega fi by 2, right? And this is the t square will get cancelled. This value will get cancelled, and this t will come here, and then we can use this formula. So this is going to be RFI value is going to be pi VFI mod square upon h cut square and pi by 2. Okay, delta omega Fi by 2. This is the delta, and Fi value we know, right? This is EF minus EI by 2h cut, right? Since we know, put value here, and now we can use property of Dirac delta. So this is RFI value is going to be pi VFI mod square upon h cut square, okay, and this is going to be 1 upon 2h cut and delta EF minus EI. This is Dirac delta property, guys, we know, right? This is delta kx. This value is 1 upon mod k delta x, right? This property we know. Okay, so the value is going to be now. So from here, PFI value is PFI transition probability is going to be 2 pi. Okay, my apology, first RFI. Okay. So value of RFI is going to be pi 2 pi 2 pi upon h cut, right? Because h cut will get cancelled, right? One h cut will get cancelled. 2 pi upon h cut, okay, and VFI mod square of VFI into delta EF minus EI, right? EF minus EI. Okay, so from here, so now we know PFI equal to T into RFI, right? So this is going to be 2 pi T upon h cut VFI mod square delta EF minus EI. Okay, from here PFI. From here PFI is proportional to T, we can see. So if T tends to 0, then transition probability is going to be proportional to T, and if T tends to 0, then transition probability is going to be square of time, right? This one. Well, this is about the dependent perturbation theory, right? So let me just check the time. Okay. So this is one question I'm going to solve for you. This is important question. Okay, this is asked in 2000 CSIR net 2017. Okay, CSIR net 2017 question, and this is a June question. Okay, this is related to transition probability. Okay, so this is a constant perturbation, a constant perturbation, a constant perturbation is h dash is applied to a system, is applied to a system, applied to a system for time t. Okay, for time t, where h dash delta t is less equal to h cut. Okay, leading to transition from transition from a state with leading to a transition from a state with EI to another another state, to another with energy EF. Okay, if the time of application is doubled, okay, constant perturbation we have applied as this for time t, so that leading the transition from initial state to final energy state. Now it is saying if the time of application is doubled, if the time of application is doubled, the probability of transition of the probability of probability of transition, okay, that is transition probability of transition will be, okay, number A unchanged, B doubled, C this is quadrupled, quadrupled, and D halved, okay. So this is the question. A constant perturbation as dash is applied to a system for time t, okay, uh, leading to a transition from state EI to another state EF, okay. If the time of application is doubled, then what will be the transition probability? That's what it is asking, right? So we know P is transition probability is PFI is proportional to T square, right? PFI proportional to T square, right? This we know. Okay. So from here, uh, P1 Fi upon P2 Fi going to be T1 upon T2, right? So P1 Fi upon P2 Fi is going to be this time is T now, okay, and now we have double the time, it is 2T, this whole square, okay, whole square, whole square. So it means 1 by 4 implies uh, P2 Fi, that transition probability is going to be 4 of P Fi, right? P1 Fi. So which option is matching? That is quadrupled, right? Quadrupled. 4 times it will be. If we double the time, then the transition probability is going to be quadrupled. Okay. Very easy question, right? We have easily solved it. Okay. Well, guys, before ending the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, rest we'll do in next uh, class. Okay, okay, guys, thank you so much. Bye now.